And this talk is about an RLC paper that unfortunately I'm not able to go and present. So this short talk would serve as a teaser for the paper. How do I make this go up? Okay, so the summary, the take-home message of the entire talk is that not all samples or experiences are equally important or useful for learning, because, yes?
Try go to more.
More here?
On the right, I'll go to the right.
Uh-huh.
Hide video.
Hide video.
No, the other way. Hide floating controls.
Cool, nice, thank you. Okay, so not every piece of experience is equally important for learning. We tend to learn more from like exciting or rare events than common day-to-day pieces of experience in our life. So we want an intelligent agent to be able to do that, to identify and learn from specific important events. How this is usually done these days in deep reinforcement learning is that we have a replay buffer and we sample experiences and learn from them. How it is most commonly done is that we pay the same attention to all the samples in the buffer. The alternative, the prioritized experience replay that we will talk about later, has a lot of different hyperparameters. It's a complicated method. It seems like a first version of a method, not a full solution, with mixed results. So I wanted to go back to the basics, pick the naive version, the basic version of prioritizing, and do experiments on there. One experiment that I will show is about a simple chain MDP where prioritization should help, but when we combine it with a neural network, it leads to undesirable learning behavior. And this is perhaps compounded by bootstrapping, and we will see an experiment in support of that later. So basically all of the results in this paper and the papers that have come before shows that maybe we need to rethink how we select samples for learning in deep reinforcement learning. So I'll start by talking about the RL problem and how it's used with experience replay these days. Then I'll talk about prioritized experience replay and all the different components that go into it. Finally, I'll show one experiment from the paper that shows this failure case in a simple MDP. So at the beginning, we have the usual environment-agent interaction. The environment shows an observation to the agent, and the agent, based on that, picks an action using its policy. Then the action is affected on the environment changes and returns a scalar reward signal back to the agent. The objective sometimes is to find a policy that maximizes the total future reward. Some other times, the objective is to learn a value function for a fixed policy. Here, we show some of the results in the other papers. It's about learning a good policy. The experiment that I do is about learning a good value function. So most commonly, these tasks are performed using temporal difference learning. You take one tuple of experience, this interaction loop, and then find a value out of that called the TD error, which is that delta value, and use that to update your value function or your policy. So with experience replay specifically, inside of the agent, we have a vector, we have a memory. This is a first in, first out buffer that keeps a certain number of most recent samples. And then each time that you see a new one, you store a new sample there, and then you sample a mini batch from the experiences already in the buffer, and you use that to update the policy or the value function, depending on the problem. Specifically, the most common way this is done is that the sampling is done with replacement with equal probability. So every tuple piece of experience in the buffer has the same probability of being sampled. So here I'll show one experiment at the end that talks about not equal probability sampling. And then in the paper, there are more experiments about sampling with or without replacement, and that has an effect on learning. So in the experiment section, I will call this basic method uniform replay. So why do we even need this? Based on all of the evidence that we've seen in the past several years, conventional neural networks don't seem to be enough for the reinforcement learning problem because of many reasons. these might be some of the reasons. If you just use one sample to make an update, maybe it's a noisy update, and that doesn't play nice with the neural network. Maybe you keep focusing on recent samples, and then the network suddenly loses learned information about long ago events. And this is sometimes called forgetting. And also maybe just doing one update with each sample is not really data efficient or a smart way to use the data. If we just do one update and then lose the sample, and it could be used more than once. So what experience replay does is that it does not tackle each of these problems fully, but it somewhat mitigates all of these problems. Because of a replay buffer, you can have a mini batch to average out the noise in the updates. Because of a replay buffer, you hold on to the history to some extent and can sample pieces of experience that are a bit in the past to keep learning from them and not forget them. And because you hold on to the samples, you can resample them more than once for better data efficiency or sample efficiency. But of course, I'm saying that maybe uniform sampling that is very common is not good enough. And why I'm saying that is that, so back in model-based RL land, we have this problem called search control, is that if you have a model of your environment, you have to tackle this, you have to basically answer this. Where do I want to plan from? Which states are useful for learning? And of course, you can have something similar to uniform replay where you pick states at random in your model. The alternative is called prioritized sweeping, where you focus on those states that led to large TD errors. And because there's a large TD error there is things to be learned from that piece of experience, and focusing on that improves the rate at which these learned information about the value can propagate back in the states. So this is one example from the book and the original prioritized sweeping paper, where you have to navigate a rod in this like maze of obstacles. And this is to show that it's possible for an environment to have many states, because there's a lot of ways that the rod can move and navigate this space. The number of states is exponentially large. And yet they showed that with prioritized sweeping, they managed to solve this problem, where with random experience selection or random search control, that may have not been possible. So we want to use, or we have been using the same intuition, but for experience replay. How that usually works, or most commonly is employed, is that you start by saying, okay, I want to sample from the buffer, not uniformly, but according to a priority, but according to priorities, and these priorities are coming from the magnitude of the TD error. So basically in the buffer, you have, in addition to the experience, a number for the priority, which is in this case, magnitude of the TD error. And as each new sample arrives, you put that into the buffer, hold on to them, and then you sample your mini batch to update your policy and the value function. In this case, the only thing that's different is that the sampling is not uniform, but it's according to the priority. So the higher the priority, the more likely it is for one specific index in the buffer to be sampled. Then, because you have to compute the TD error to update the value function and the policy, you have new TD errors to update the priorities in the buffer. That loops keeps the priorities, at least for the experiences that are being selected, somewhat up to date. So this seems to be the most basic way to pick that idea from prioritized sweeping and put it in experience replay. I will call this naive PER, or prioritized experience replay. Why? Because, well, prioritized experience replay, PER itself in DeepRL is this, plus some other things that I will talk about now. So we take this basic approach, and then we add on top of it more components that add complexity, that add hyperparameters, and so several of them somewhat turn the replay somewhat back to uniform replay, as you will see now. There's another hyperparameter that dampens the priorities. That's a hyperparameter. Basically, the exponent is a hyperparameter less than 1, needs to be set by the experimenter, by the designer, that lessens the spikiness of the priorities, makes it more like uniform. They explicitly combine the prioritized probabilities and the uniform priorities, uniform probabilities with another hyperparameter, basically a mixture of the two. And that, of course, makes it more like uniform replay. Then they downweigh the size of the updates that are coming from prioritized transitions. So that means that if your sample has a larger probability of being sampled, then its magnitude when used for the update is reduced, which is kind of against the idea of focusing on certain samples because you weigh them down. So then that is also on a schedule, it changes over time, and sometimes it's normalized, sometimes it's not normalized. It's very complicated, not elegant at all. Finally, they start putting in samples in the buffer with maximum priority to basically avoid having to compute the TD error when a sample is seen or like observed. Because the priority is set to maximum, you will eventually sample it very soon and have a correct estimate of the TD error, have a correct sample of the TD error there, which again seems to save a little bit of computation power, but makes the method more complicated. So the point of this slide was to show that a very simple, easy to understand, nice idea is compounded by many additional components and several hyperparameters, making prioritized experience replay in deep RL today hard to analyze or study. So I want to go back to the very beginning, say, okay, I just want the prioritized distribution, nothing else, and talk about that. But first, let's talk about the results in the literature. So this is basically an aggregate over the Atari games from the prioritized experience replay paper itself. I mostly want to care about the black and the blue curves. The y-axis is normalized score, and the y-axis is time. You see that the blue curve, which is using PER, shows better sample efficiency because it goes up faster than the uniform curve. 2 years later, in Rainbow, they putting together several components, one of them being PER, and they showed that it performs very well again in the Atari games. But this one experiment in the paper is very nice because they show what happens to sample efficiency as you take out each part of the system. And the one that I want to care about here is the blue curve, which is Rainbow without prioritization. And now you see a big gap for the blue curve and the rainbow curve at the top, which may suggest that PER is an important factor in the rainbow architecture. So these two results are in the Atari environments. The problem is that I saw many papers that have mixed results, as in some of them in some other environments say that sometimes prioritization is better than having a normal basic random experience replay. Sometimes it's worse, sometimes it's the same, sometimes it depends on your hyperparameter selection. And so basically these papers and some of the experiments that we run in the paper ourselves that I'm not showing here says that these results are mixed, and it very much depends on the problem and the hyperparameter setting. And I don't see a clear advantage of that complicated system. So now that I'm not happy with that complicated system, I go back to the very basic one, and I want to study it in a simplified setting. That setting is a Markov chain. This Markov chain is a simple MDP where you start at the leftmost state and you have to take actions. Sometimes you go left, sometimes you go right. And then basically at the end of the chain, there's a +1 reward. This is the only reward. And the episode terminates. Then the next episode starts. And the task here is to learn the value function of the random policy. So it's policy evaluation, it's not control. And my objective here for picking this environment is that it's super simple. The only difficulty here is propagating that +1 at the end of the chain in the states. And prioritization should be helpful here because being at the end of the chain, you have that +1 sparse reward learning signal, and every other state has no reward. I think I saw a hand. No? Okay. So the method that I'm using here is TD plus a conventional deep neural network or tabular representation as an alternative plus replay. And I try the two different replay methods that I talked about in this talk, the naive PER and the uniform. And the metric, the score that I want to minimize is mean squared value error that shows the quality of the learned value function. And here we can directly compute it because the environment is tabular and we have access to the real dynamics of the environment. We can have the actual mean squared value error. And so that DS is also the stationary state distribution under the behavior policy, which in this case is also the target policy. It's the random uniform policy. Let's talk about some of the results. The very interesting part here is that prioritization can lead to value overestimation. Let's talk about it. So these two curves show mean squared value error, which means lower is better, and the x-axis are time. We have two curves. The black one is the uniform replay. The red one is the naive, the simplified version to do prioritized replay. In the tabular setting, it performs as we expect. We want faster learning, so the loss comes down quicker, and it's what's happening. Using prioritized replay improves the sample efficiency in the tabular setting. But with neural network, we see that spike in the value error is happening like kind of at the beginning, whereas with the uniform, we don't see that. So I was kind of interested in why that is happening. I thought maybe it's poor hyperparameter choice. So I changed the size of the network or the batch size or the buffer size. I swept the step size. I changed everything. And then in every setting, the only thing that's different is basically the placement of the spike. And it always happens. So I thought maybe that's not the issue. So the next step was to actually visualize the value function and see what's happening. So these are heat maps of the value function. These are temporal heat maps. So the x-axis is again time synced with the curves, and the y-axis are the states in the chain. The leftmost state is the bottommost row, and the topmost row is the final state in the chain. And so the +1 reward is happening at the topmost row in this heat map. And the heat map is basically scanned left to right as you move forward in time and then update your value function. So in the left heat map, we see that using, these heat maps are for naive PER. That's the only one that I'm showing here. We see this propagation of information about the value from the end of the chain down in the chain. And that's this thing happening. That's kind of what we want. But with a neural network, first of all, it's much more noisy. Sometimes the value is negative, where it's not actually possible to have negative value in this problem. And there's a lot of change and noise during learning. But specifically, I want to focus on this light band that happens at the same time as the spike in the TD error that seem to suggest that the network is predicting a larger value than correct for all the states. So my guess here is that because you prioritize those samples at the end of the chain, those with the large TD error, and you do more updates with them, the entire network is seeing the +1 for the reward. And so seems to move the entire prediction of the network toward that +1, basically an overestimation. So that's not good. That's not what you want, especially in this simple of a problem and this simple of method. So I thought maybe the problem is due to TD. It's not because of just because of the network. It's because of the combination of these two. So the next hypothesis is that this value over estimation is at least increased or compounded by bootstrapping. So how we test this is with a target network. Target network is usually employed in off-policy control, for example, in DQN, to stabilize learning to some success. But here, I don't want to use it as a mitigation or a way to solve it, but as a tool to slow down the effect of bootstrapping, because you can hold the target frozen for longer. So that is the TD error that you saw earlier. And that one part of TD error is the prediction being used as a target of the update. And so if you keep that frozen for longer, then you effectively make bootstrapping less of an important player and turn the problem into a sequence of supervised learning problems. So these two curves, this curve and the heat map, they are copy pasted from the previous slide. That one there, it means that the targets, the frozen part of the TD error is being updated on every step. Now, these two other curves and their heat map shows what happens as you increase this frequency at which you renew your targets. So you have a larger update time, or like refresh rate. 100 means you update it after 100 steps. So now you see, as you decrease the effect of bootstrapping, that spike starts to decrease, and the light band in the value function also goes down and slowly goes away as you increase the target refresh rate more and more. Of course, this is not a way to solve it. It's just a way to show that bootstrapping is playing a role there. So this again shows that even the simplified method, even on a simple problem, there's problems. And we need to address these problems at some point. So I don't want to show more experiments and point you guys to the paper, but I wanted to talk about the entire talk once more at the end, that we care about certain pieces of experience more than others, and an intelligent agent should be able to learn from them and find them. In deep RL, we can use experience replay to effectively decouple the process of data gathering and behaving from the process of learning. And now we have the possibility to use search control over the replay buffer to pick and choose which of these samples is more important for us. The one alternative to random replay that is seeing some attention in deep RL is prioritized experience replay. It's a complicated algorithm based on a very nice design, but it compounds the base method by adding hyperparameters and some components that are not very much aligned with the whole point of choosing certain samples or learning more often from some samples. And some of the later results in the other papers and this one show that that method is not good enough. And the experiments that I showed here also show that there is a bigger problem that needs to be addressed when it comes to selecting and prioritizing samples in deep RL. There are a lot more experiments in the paper. There's experiments with noisy environments, and we have a variant of PER that is more robust to noise. There's experiments with sampling each item in the mini batch without replacement or with replacement. And that is important. If the priority is focusing on certain samples, it's possible to saturate the mini batch with just a couple of samples, and that is not very good. Now, also, we have experiments that update the priority in the buffer to see if stale priorities might be a part of the issue. That's the link to the paper. Please check it out at RLC. Thank you. Yes.
So prioritized experience replay involves computing the priorities. The priorities are TD errors, absolute values of the TD errors for all the transitions in the replay buffer. And but I can't believe it's literally that, because if you literally do that, you have to do it's so much computation. Like every time, after every update of the network, you have to go through the entire replay buffer and do 2 forward passes for everything. That's
right. So how it's usually done in deep RL is this: you start putting the priority of each new sample as maximum, as this is the highest priority. So then that means that it will be sampled soon because its priority is manually set to maximum. When it is sampled, because you want to use it for updates, you will compute its TD error, and that will be its priority. And the priority of the entire buffer is not refreshed at every point. The priority of just the mini batch is updated. That's how it's done in deep RL. Yes.
I'm just confused what the algorithm is.
So
You said very clear explanation. You use the absolute values and TD errors.
yes, yeah.
That's all. That's all wrong. It's in fact nothing to do with that.
Okay, so when you see a new sample, it's possible to basically insert the sample with its TD error, correct? It's possible that you don't want to find this number because it's costly. Instead, you set its priority to be maximal, the highest value. That forces the sample to be chosen next time. And then because you want to update or learn from it, you will have to compute its TD error. From now on, its priority is the real priority, the TD error. So in the naive PR variant, I did not do that. I actually compute the TD error when I see the sample for the first time. However, when I
don't you have to recompute the delta every time you do an update to any weight in the network?
Right. So, okay. No, in deep RL, they do not do that. And this simplified version also does not do that. But yes, I agree that having up-to-date priorities is very important. And there are experiments in the paper that investigates that. And of course, again, sometimes it helps, sometimes it doesn't, especially with a neural network. Mostly it doesn't.
Okay, thanks.
Yes.
Cool talk. I have a couple low-level questions regarding the experiments.
Yes.
First, what type of policy was used in the chain environment?
It's random uniform policy. And basically it's a policy evaluation with a fixed random policy. Okay. And the task is on policy evaluation.
Okay. And then the other question I had was about the prioritized experience replay with varying target network update rates. You can kind of see that like the sample efficiency benefit kind of goes down as you increase the target network update rate. But the uniform one, that's always with the rate of 1.
Yes.
Do you know if you increase the target network, does the uniform also slow down like substantially? Are there benefits at that high?
I have not tested, but my guess is that yes, it will slow it down because the value propagation that happens because of TD is basically what is helping the value function be more accurate across the states. And if you slow that down, then that slows down the progress in the propagation. So I have not tested it, but yes, that's my guess, that as you increase the target refresh rates, then that will also slow down the uniform replay. Any other questions?
There's one person
Online question. Do I open up my speaker?
Hello.
Hello.
I've got 2 short questions. First is, do you expect that you would see the same sort of value overestimation if you used linear function approximation in your problem? Is it really just an issue with function approximation as opposed to the neural net? And the second question is really a more general notion, which is prioritized experience replay is changing the distribution of samples, which we would also see when we do planning, as in prioritized sweeping, right? And so when we think about planning with function approximation, we're going to have we would want to be more agnostic to the distribution than we are during learning. So the second question is more open-ended, but the first question is really, yeah, do you expect to see the same effects with linear function approximation?
Right. So I think that if you want to use a linear function approximation, that really depends on the features. So part of this problem, at least in my opinion, is that a network very much has no structure, especially at the beginning. And then if it just sees that one experience at the end of the chain over and over again, much more often than anything else, from its point of view, that's what the world is. And everything has a +1 reward. And that's why it updates it towards that. With a linear function approximation, if the features are like nicely local, like tile coding, I would assume that this does not happen. But if the features are very bad, for example, a network that is recently initialized and frozen, then probably it would still happen. For the second point, which is about, well, what happens with the state distribution, well, I'm not really sure, but I do have some points, and that is that one thing that in deep conventional PER they do is this third point here, is that they use importance sampling weights to re-weight the updates, to change the state distribution. However, note that this is not the same kind of state reweighting as we do for off-policy learning, because in that case, you are changing the state distribution of the next state. But here, they use it to change the state distribution of the starting state, of the current state. And so basically, this problem is called prior correction or posterior correction. My understanding is that we don't really know what a good prior should be, because there's evidence that it's the emphatic weighting, or maybe it's the behavior policy, maybe it's the target policy. I'm not really sure. But yeah, that's my take on the state distribution. Yes.
I'd like to ask a couple more questions about the experiments too.
Mm-hmm.
The state, so the problem being faced is in principle represented as a tabular problem, but when you use a neural network, you have some feature representation for the states.
Mm-hmm.
What is that feature representation?
So it's basically I wanted to not help the network at all. So at the beginning, the features are one hot.
Okay.
And then the network must learn to represent it nicely. So it's also possible to use like nicer features, like dependent features, and then feed that into the network. That will still have this problem with the network.
And so I think you wouldn't really expect generalization between states with the one hot representation. Is that right?
Well, if you just have the one hot and the linear weights on that, then you wouldn't. But if that is fed into a network, as it is in this experiment, in the right plot, then yes, that the one hot representation is fed into the network. Now, because all of the weights are interconnected, now everything changes. But in the tabular version, it is just the one hot. So it's tabular. It stays disentangled. Yes.
Thank you for your presentation. I'm kind of new with possible learning, but I have just one curiosity. Have you ever try with different types of Markov chain? Like, because I don't know how you call here in Canada, but in Brazil we call that cemetery state, that final one that if you add infinito, it goes to the final state.
Mm-hmm.
But if you don't have this final state, what would be the difference?
Right. So I did tests with a lot of variants in the chain. Mainly, I tested noisy chain, as in it's the same one, but sometimes you choose to go to left, but instead you go to right. Or sometimes the +1 at the end is actually much larger, or sometimes smaller, but the on average it stays the same. That is one set of variants. We still see the same problem there. I changed the length of the chain, the same thing. I did not use some kind of non-episodic problem. My understanding is that what you said is that at the end, instead of terminating the episode,
Go back to the first state.
you go back to
Yes.
the first state. So that's a non-episodic problem. I have not tested with a non-episodic problem.
Okay.
Yes.
Do you know about the work of Pang and Williams?
Or perhaps if you say the name of the paper.
So the thing is, let me just correct the record. So the inventors of prioritized sweeping are Pang and Williams and X and Moore, two papers published at the exact same time. And the thing about X and Moore, they use the name prioritized sweeping, but it's the exact same thing at the exact same time by Pang and Williams. And so, you know, we should refer to both of them equally.
Right. Okay.
And you should know about both.
Okay.
equally.
Pang and Williams.
It's in the book.
Okay. Okay. Cool.
We can't just cite the people who use the name that
Yep.
we use, the only name that we know about.
That's very correct. Thank you. Pang and Williams. Yes.
You plotted in your nice graphs, you plotted the test error. It's essentially test error, right?
Test error. I don't know what that means. It's the I have the agent.
Instead of D is computed analytically.
This D?
Yes.
Yes.
What if I change it with I just tested on samples which are in the data? Then results will stay the same.
Okay, so if you tested with if you just use the samples that you see, then I expect the state distribution that you end up observing is weighted by the behavior policy, correct?
Yes.
And here, behavior and the target policies are the same, and it's the uniform policy. And this is exactly the correct state weighting under the random policy. So I expect that it would be similar to this, or like as you increase the size of your data sets, it would be more and more similar to this. I also note that the state weighting is not uniform across states, because some states that are like the left states are easier to reach, and their weighting would be higher.